let's continue with the following example of a function t from R3 to R3. So it takes a vector in R3 and produces a new vector in R3, which is given by the following formula. So t will send the vector x, y, z to the following vector. So let's say we take x plus 2y, 3x minus absolute value of z, and 4z, for instance. Okay, and the question is, well, is this function a linear transformation? Well, to check this, well, we have to see if both axioms and the definition of a linear transformations are satisfied. So a priori, well, this is not entirely clear, but remember that in linear algebra, what are the operations that we are allowed to do? Well, it's with vectors, it's addition and scalar multiplication. Okay, and if we look here, well, on the first component and third component, we've got also just addition of numbers and scalar multiplication. Okay, so you can multiply these variables by some scalar. But in the second component, we have this absolute value. And absolute value of z is not something linear. So the only linear functions from the real numbers to the real numbers are of the form f of x equals ax. Okay, and their graphs are just lines going through the origin. So these are the linear transformations from R to R. Absolute value is not linear. Its graph is not a line. Its graph is it's a V like this. Okay, so looking at this, it suggests that this function t is not going to be a linear transformation, and what causes the problem is the absolute value here. Okay, so this is indeed the case. I could have replaced absolute value by some other function which is not linear, like z squared, z cubed, or xy, or sine, or an exponential, etc. So they are, most functions actually are not linear. So producing functions that are not linear is not difficult. Okay, so all right. So looking at this, so we can suppose that indeed this function is not a linear transformation. So to show this, well, we have to see that at least one of the two conditions, two axioms, and the definition of a linear transformation are not satisfied. Okay, it could be that both are not satisfied, or maybe the one about scalar multiplication is satisfied, but not the one about addition. Well, in this case, neither of them is satisfied. And to see this, well, sometimes you can check this in general, but it's enough to give here a just one counterexample, right? So if you, in the next example, we will have to prove that some function is a linear transformation. Then you have to prove things for any vector x, y, z. But if you want to show that something is not true, it's enough to just give one specific example that shows that it's not, that one of the axiom is not satisfied. Okay, so you can call this a counterexample. And for a counterexample, you can give x, y, and z some specific values. Okay, so, all right. So we should, okay, but then the question becomes, what value should we look at? Well, sometimes if you're not sure, you may, just try some. Sometimes can make a guess, try values that are not too simple, like you don't try to try them all to be zeros, or to be ones, okay? Sometimes even if you're not sure exactly how to build your counterexample, you can just try something a bit at random with some small numbers, maybe both positive or negative, and see if the axioms in that specific case are satisfied or not. So here, because we have absolute value, well, the absolute value of z is just z if z is positive. Okay, so if I'm restricting to examples where z is positive, this becomes just z and it looks like it's linear. So if I want to get some good counterexample, maybe I have to look at cases where the value of z is negative. Okay, so right. So okay, so let's try something. So here, I mean, I could even give x and y value 0. So right. So the condition we want to satisfy, right? There was the first condition, right, that we had previously is t of u plus v equal to t of u plus t of v. All right. So we need to make some good choices for u and v. So, all right. So for u, I said the z entries for at least one of these vectors should be negative. Okay, x and y don't create too much trouble here, so maybe let's just give them value 0. Okay, so let's try to, for u, the following vector. Okay, so if you need a counterexample, in general, no need for something too complicated. Okay, so this is u. I want to apply t to this. Well, here, in checking this identity, sometimes you start with the left-hand side. Here I'm starting with the right-hand side. Okay, so I'll have t of u. I also need a t of v. Okay. So what should v be? Well, let's see. If v is 0, 0, 1, I'll get the sum will be the 0 vector. And t of 0 is 0. Okay, maybe let's try this. And see what happens. Right, so here when I write this, it means first I will apply t to both of these vectors. Okay, so if I apply t to this vector, I get 0. Then here I get negative absolute value of negative 1. Absolute value of negative 1 is 1, and I'll get minus 1 here. And finally here I get minus 4. Okay, what about this vector? Well, x and y are 0 again. Here, well, I get absolute value of 1 is 1, and I get a minus sign in front. And the last entry is a 4. So I get this, and now I just sum these two vectors, and we get 0, negative 2, 0. All right, so this is the right-hand side there. Right, what about the left-hand side? Right, so this is, I said this is this vector, this is u, this is v. Right, so in this case, u plus v is the 0 vector. Right, so let's see, because I want to write this here. So in this specific case, we get that u plus v is the 0 vector. Okay. So, and t of 0 is going to be 0. If x, y, and z are 0, t of 0 is 0. Right? Actually, this is true for any linear transformation. It always sends the 0 vector to the 0 vector. So if you have a function that doesn't have this property, then for sure it is not a linear transformation. It's probably the first test to check to see if some function is linear or not. Okay, so here, well, t of 0 is 0. Right, so if I'm looking, right, so t of 0 is 0, which is not this vector, right? So this is not equal to the 0 vector, which is t applied to the 0 vector, which is u plus v, right? So this 0 vector, this is the u plus v. So this shows that in this case, right, maybe I could have put a question mark here because I wanted to check this. Is this satisfied? If that property is it satisfied for all vectors u and v in R3? The answer is no. Here is one counterexample. When u is 0, 0, negative 1, and v is 0, 0, 1, right, I can compute this t of u plus t of v, I get 0, negative 2, 0. It's not the same thing as t of the sum, right? Again, this 0 vector, it is the u plus v. Okay, so here, right? So this T of u plus v, it's exactly what we've got here, right? And the T of u plus T of v, this is what I just computed that I started with. So it's what is there. And these two vectors are clearly different, okay? So in this case, it means that, yeah, these two are actually different. Okay, so consequently, this function is not linear. Okay. Another way to see this would be to use to see that the second axiom and the definition of a linear transformation is not satisfied. And so that one has to do with some scalar and just one vector v or u. So either, well, one can check that this property is not satisfied in general, but it's actually enough to see that it's not satisfied in one case. So let's try to see this. Again, because of the absolute value, one can suspect that, if you give the scalar some negative value, then maybe this will not work, right? So the other condition, I mean, we don't have to do it here. I'm just doing this because that's another way to check that t is not linear. So, right. So the other axiom is this: t of c times v equals to c times t of v. Okay, and one can ask, well, is this true in this case? Okay, I could have started with this. So, right. So because of the absolute value, I'm suggesting maybe we should give c some negative value. So what about giving c value -1? And for v, well, I'll keep the same v and see what happens, right? So if we do this here, so we can calculate t of c, which is -1 times v. For v, I'll keep 0, 0, 1. Right? So here, first I have to do what's inside the parentheses before I apply t. Right? So what is this vector? Well, this is the vector 0, 0, -1. Okay, and well, we already computed t applied to it. It's going to be this vector. So this is 0, -1, and -4. Okay, what about the right-hand side? What is c times t of v? Well, when v is this vector, t of v is this one. Okay, so here we can see that this will be, well, I'll compute this here. What is t of, well, what is c times t of v, right? So v is 0, 0, 1, right? So 0, 0, 1. Okay, c is -1, so I put a -1 in front. Okay, well, is this equal to that? I mean, is this, right? So here, I computed this here. Okay, and I got this vector. Now I want to check if it's equal to this. So I'm going to compute this here. Okay, and right, so t of 0, 0, 1 is actually this vector. Okay, 0, -1, 4. So I still have the minus sign in front, and then I get 0, -1, 4. Okay, and now if I put the minus sign inside the vector, right, so I've got the minus sign outside, I just changed all the signs inside the vector, so I get 0, 1, -4. Okay, like this. All right, and now, well, is this vector the same as that one? Right, so if you look at this vector and this one, right, so we see that these two vectors are different. Okay, so this is different from this one. Okay, so it means that, yeah, well, what I've got here on one side, it's different from what I've got there. So it means that here, this is not an equality also, right? When you take c to be -1 and v to be this vector, so this is not always true. To show it's not always true, you only have to show it's not true for one specific scalar c and one specific vector v. Okay, so these are different. Okay, and the conclusion of all of these is that, yeah, t is not linear. So t is not a linear transformation. Okay, so I'll write this down here. T is not a linear transformation. Okay, and it was enough to check either for addition or just either scalar multiplication. I did both, okay, but you normally, you will only have to do one of these two, okay, and which one you do, well, most of the time you pick which one you prefer, okay, so.